So good evening, all of you. I am Dr. Ravi Sirbara. So first session expert, Bhavesh, Dr. Bhavesh R. Bhalja is working as a professor and head Department of Electrical Engineering, Institute of Indian Institute of Technology, IIT Roorkee. He has teaching experience of more than 25 years. He has published more than 150 papers in journal at international and national levels. He received Fulbright Nehru Academic and Professional Excellence Fellowship and worked as a visiting scholar at Department of Electrical and Computer Engineering, Texas University, US, for a period of 9 months in 2018 to 2019 in area of fault detection using synchrophasors. He has been awarded Young Engineer Award, Certificate of Merit Award, Pandit Madan Mohan Malaviya Memorable Prize by Institute of Engineer India in 2009, 2007 and 2016 respectively. He has written 4 books in electrical engineering published by Oxford University, Springer, Science Business Media Singapore and elsewhere USA. He has also written 5 book chapters on artificial intelligence application in electrical engineering published by CRC Press, Taylor and Francis Group. He has developed 2 online courses on power system protection and switchgear in 2020 and digital protection of power system in 2022. He has also worked as an Associate Dean of Academic Affairs Evolution IIT Roorkee from September 2020 to August 2023. Currently, he is involved in 6 research and industry funded projects worth of 50 million, including Ahmedabad, Mumbai bullet train, Kalka Simla heritage train, and smart charging infrastructure of electric vehicles. He has guided more than 50 undergraduate projects, 30 postgraduate projects, and 20 doctoral students. His research interests include digital protection and automation, smart grid technologies and applications, cyber security, distributed generation, microgrid, phasor measurement unit, condition monitoring of electric apparatus and application of artificial intelligence. Sir, we welcome you, sir. Please, you can start your session, sir.
Welcome, sir.
Okay, just a minute. Is it visible now?
Yes, sir.
Yeah.
Yes.
Okay, fine. Shall I start?
Yes, sir.
Yeah, so just 2 things. I hope the screen is visible and I'm also audible, right? Ravi? Hello, Ravi, am I audible?
Yes, sir. You are audible.
Okay, fine. Okay, so I think the today's session was related to the fault classification in power systems with some machine learning algorithms or AI or ML based algorithms. Now, before I move, my presentation will have two things because I need to discuss few things which needs which you can say it is acting as a prerequisite of the subject, right? So this fault classification in power system that comes under the umbrella of the protection and switchgear. So those who have studied protection and switchgear at UG level, they are well familiar with this subject. However, hurriedly just for 15-20 minutes, I will go through it and then I will share another PPT which deals with the fault classification part. Now, before we move, we know that our power system network is highly volatile in nature. Earlier, it was only the power flow that is there from one side to another side. So we can say it is a unidirectional power flow. Later on, when the restructuring of power system took place and the addition of renewable energy sources were also there in the system, then it does not remain unidirectional. So it becomes the bidirectional. So when the system becomes bidirectional, then we are going to face several challenges. Of course, fault classification part in power system is a very broad topic. Uh, I worked this topic just I think 12 years ago during my PhD. And thereafter, I did not work on transmission line. Of course, I worked on microgrid and some other area, but EVs and all that, but not this conventional one because there is lots of research papers and the technology transfer that has been taken place and the scope that is very limited in this area, right? If you just look at the transmission line, then the scope is very limited. If you look at some other areas like microgrid, nanogrid, HVDC, then the scope is still it is there and people are working in this area. Now, if you just look at the protective device, conventional, whether we use fuse, MCB or relay, right, which is used for sensing the fault, that remains same whether we use for AC system or DC system. And along with that, the relay, MCB or fuse, of course, if we remove the fuse, then MCB and relay that is meant for only sensing of the fault. The isolation task that is to be performed by some other device known as circuit breaker. So same way in AC or DC system, we do have the similar type of mechanism. Now, why we need fault classification? Number one. So we know that whenever the fault occurs, obviously there is an interruption of power supply to the consumers. Consumers, those are not going to get the supply. On the other hand, the utility or we can say state electricity board that is going to have the loss of revenue. And of course, at equipment level or the system level, we have the loss of synchronism or the damage to the equipment. And of course, the hazard to the personnel, which is very least bother. We do not bother about this in our country. So if you decide or design any system, then the first is you have to design a system which is capable to detect the fault, whether it is anywhere on the system, AC side, DC side, anywhere. And then once it is detected, then you have to de-energize the faulty section without affecting the healthy part. And once isolation is done, then the next part, last phase of the part or the task we can say that comes in picture. That is the what is the type of fault and what is the location of fault. At what location fault has occurred. So class fault classification that is nothing but we need to know which type of fault has occurred. And the second thing is for maintenance purpose, obviously engineer needs to know that at what location fault has occurred so that maintenance that is to be carried out. Now we will come later on this part. Now if we look at hurriedly, there are two types of faults, symmetrical faults and asymmetrical faults. If you just consider symmetrical faults, triple line, three phase, we can say fault, either triple line or triple line to ground. It may or may not involve the small amount of resistance. Otherwise, if it is not involved, then it is bolted short circuit, we can say. And asymmetrical faults, we are well aware, maybe line to ground three types, double line three types, double line to ground three types, right? And we have not considered here any open conductor faults, that comes under the different category. Now, if you just consider the symmetrical fault, then nowadays symmetrical faults are very rare. Earlier it was there 10, 12, 13, 15 years ago. Nowadays it is not there. The reason why symmetrical fault or three-phase fault occurs, the reason is we are using earthing switch at each end, either sending end or receiving end or local end or remote end. And whenever something goes wrong, fault occurs, then we need to open the circuit breaker at local end, same way circuit breaker at remote end. And when we need to carry out the maintenance, and after that when you want to restore the supply, at that time earthing switch comes in picture. So if earthing switch is on, let's say, right, both the sides, and if you try to energize the transmission line, then there is a bolted three-phase short circuit occurs. However, I said just a minute ago, it is not possible. It is very rare, rarest of the rare, I can say. The reason is there is a mechanical interlocking or an electrical interlocking provided by the utility. So if you try to energize the line, assuming that earthing switch is on somehow due to some reason, then you are not allowed to energize the line. Such type of interlocking that is already there. So this is not there. Why we bother about symmetrical fault? The magnitude of current is very high, let's say 10 times. The vector sum is zero, so no current passes through the ground, right? The only issue is the over voltages. And if you consider the asymmetrical fault, then the, let's say, line to line fault occurs because of the bridging of two conductors. Either it may happen in the machines, let's say AC, DC or any other machines, or it may happen in the transformer also, terminal of the transformer, uh, or maybe because of the failure of insulation between the two conductors. So we know that when the during monsoon season or some specific condition, let's say when some cyclone is there uh, and wind is very severe in nature, then the swinging of conductors take place, and this may create the line to line fault. However, line to line fault is not going to occur because of birds, kite string or tree limbs, right? Because the height of the conductor, if you consider, then that is very high. And if you just look at the spacing among the among the different phases at different voltage level, 66 kV, you can say. I have mentioned the spacing depending upon the vertical or horizontal configuration we use. And this spacing is usually in mm, right? And you can see as you go on increasing the voltage level, this spacing goes on increasing. And if you just look at the 400 kV, then the spacing is very high, right? You can say it is close to, let's say, very high, almost close to 8 to 10 meters or 12 to 16 meters if you use horizontal spacing. So chances of line to line faults are very rare, right? That is not there. And if you just look at how to calculate the spacing, so then that I have calculated using the several formulas are available. Macom's formula, VDE formula, Macom's formula that is used by French, VDE formula that is used by Swedish utility, and still formulas and so on. So I'm not going in detail, right, that how they are going to conduct, consider or calculate the this phasing between the conductors. Of course, whenever you have ice loading or some special condition in developed countries, their offset that need to be given, and that is also given by this standard empirical formulas. Then becomes ground clearance. So ground clearance also plays an important role. And if you just look at the Indian system, as per our IE rules 56 rule 77 by 4, we need to have the ground clearance of the order of depending upon what voltage level we have. So if you consider 400 kV, ground clearance is close to 9 meters from the ground, and 765 kV it is close to 14 meters, right? So that is also very high. And if you have, let's say, some railway tracks or all that, then also you can consider the calculate the ground clearance using different formulas. So I am not going in that detail because this I think I hope it is already known. Now, why we bother about phasing between the conductors and the ground clearance? Because these two factors are important for the consideration when we consider the any type of fault. Usually 90% faults are asymmetrical in nature, 90 to 95%. So again 90% are single line to ground. So we are more concerned about single line to ground. So this may happen because single line to ground fault occurs because of flashover across the insulators, failure of insulators due to lightning or switching surges, and if defective insulators are there, which are very rare. Now, if you consider the first part, the most of the line to ground fault occurs because of flashover across the line insulators. So if you look at here, right, the figure, then I have shown the group of or string of insulators. It is each disc voltage is 11 kV, and you can calculate the depending upon the what voltage level you have used. Let's say 132 kV, then 132 kV divided by root 3 because it is connected between the live and the cross arm, which is at ground level. So 132 kV divided by root 3 divided by the rating of each insulator, so 11 kV. So based on that, you can calculate the how many number of insulators are required. Now when so if you just look at right different voltage level 66, 132, 220, 400, then the number of insulators required are shown here, right? So I have written in the range, not exact value, because you have to consider factor of safety also. And you have to also make the calculation, the integer value. If it comes real value, sorry, floating value, then you have to consider it integer, considering factor of safety. So if you just consider this figure, now your let's say your conductor is at lower one 132 kV conductor, and on upper side where the first string of insulator is there, and we know that for 132 kV 9 to 11 insulators are there. So here you have 9 or 11 insulators. Now if there is a lightning surge occurs here right at this point, so like whenever lightning surge occurs, it is normally the study indicates that the magnitude of current that may vary from 150 kiloamps to 250 kiloamps. So if you look at the 150 or 250, let's say average it 200 kiloampere, multiply by some very nominal value of resistance. So 200 kV, let's say that is appear when lightning surge occurs here at this point, and at lower point you have the let's say 132 kV. So if you take let's say worst case 220 minus of 132 kV, right? Then the voltage becomes let's say 332 kV, and the strings right it is capable to withstand 132 kV by root 3 multiplied by root 2. So only that much value it can withstand. So if 332 kV voltage comes across this, there is a flashover across these insulators, and hence there is a from conductor to cross arm, which is at ground level, there is a line to ground fault occurs. So this is the simple way how line to ground fault occurs. So open conductor, we are not bothered about this. Now whenever let's say line to ground fault occurs, right, or triple line fault occurs, the two things which is very important. One is the thermal damage. So thermal damage is obviously it is related to the deterioration of the insulation. Obviously, whenever the fault occurs, the current becomes drastically very high. Let's say 2 to 10 times the continuous rating of the let's say conductor or any machine. So at that time, the temperature or heat produced, that is I square RT, right? So thermal damage, that is very important as far as the whenever the fault is concerned. And second damage is the electrodynamic damage. So because of let's say very high magnitude of current, very high forces are generated, and that is going to destruct the whole equipment, right? Structurally, that means your equipment may damage. So these two things happen whenever fault occurs. So our task of the engineer or utility person is to detect the fault and isolate the system before the thermal or electrodynamic damage occurs in the system, right? So that is there. If you look at the percentage of occurrence of fault, maximum fault occurs on the overhead line, let's say 50%. And if you consider the type of fault, then 90% faults are, let's say, line to ground faults. And that's why we are more bothered about this. Now, now we have established that the 90% of the total faults which are going to occur, that is, let's say, line to ground faults. Now, among this 90% of the line to ground fault, there are also classification in terms of transient and permanent faults. So let's say a total out of the total fault, let's say 90%, let's say total faults occur in a year, in a 1 year span, let's say that is 10. Now out of that 90% of 10, that is, let's say, 9 types of faults are line to ground fault. And this 9, if you consider, then the transient faults, means faults which are transient in nature, that is also 90% of 9. So close to 8 types of fault out of 10 are transient in nature. That means the fault occurs and they are going to die out after several cycles, maybe 1 cycle, 2 cycle, 3 cycles, depending upon the severity of fault and the other operating conditions. Hardly, let's say, 20% or 10% of the fault are permanent in nature, which lasts for longer duration. That may going to damage your equipment, and utility has some mechanism to detect and to isolate the break through circuit breaker whenever such type of permanent fault occurs. So that is there. Okay. Now I think yeah, one more thing. Now, whenever, let's say, you can see here our entire power system network that is divided in several zones, right? Why zones? Why not only single device? The single device is not there because the line is very long. The characteristic of each equipment that is also different, right? And non-linear in nature. Let's say a generator, power transformer. Let's say you consider bus bar, then the transmission line, and then again the transmission line is available at receiving end. Then again further distribution takes place, and so on, right? So till you start from power station to, let's say, you are available or you end at the last person, that is us consumer, right? Of course there are different types of consumer: residential or domestic, commercial, agriculture, and industrial, right? But we are not going in detail of those types of consumer. Our just task is that we need to design a system for each zone, right? If it is, let's say, fault is in transmission zone, then a dedicated system is there which can detect the fault, which can isolate the breaker of the line, and which can, let's say, also we can say that which can classify the fault, and which can also locate the fault so that transmission maintenance can be carried out. If faults are going to occur in the apparatus like generator, transformer, induction motor, bus bar, then the location is not important, right? Because it is very minimal. It is hardly within the substation only, because all these power transformer, power generators, those are within the substation or within the switchyard. So for that case, fault location is not required. Classification is required so that a person can take the necessary measures. Obviously, you have, if fault occurs in transformer, then you have to isolate the circuit breaker at both the side of the transformer, and then you have to do the maintenance. So this is already there. So the thing is that if, let's say, there is a fault occurs on transmission. Now let us just concentrate on transmission line, because we are more concerned about the fault classification and fault location part, right? Which is the title of my talk. So if we just consider the, let's say, if transmission line is there and if there is a single line to ground fault which occurs on the line, then obviously there is a fault. So some sensing mechanism is there at some bus level, local or sending end. Similar mechanism is also there at other end, receiving end. So your relay is going to sense the fault, and it is going to send a signal to its contact. Contact will further energize the auxiliary relay, and then when auxiliary relay contacts closes, then trip coil of circuit breaker is energized, and this breaker which is here, that is going to become open and fault can be isolated. Condition is that if this fault is permanent in nature, right? That is more important. Now the question comes, how utility person will identify whether the fault is transient in nature or permanent in nature, right? So the thing is that there is no such mechanism exist, right? To discriminate whether the fault is transient in nature or permanent in nature. So then what they are using? So utility people are using single phase auto reclosers, right? They are using auto reclosing devices. Auto reclosing devices is a part of this circuit breaker here. Let's say it is also here, but let us concentrate on the sending end. So whenever fault occurs here on the line, this relay is going to sense the fault. It gives signal from here to its contact. Contact closes depending upon the severity magnitude of fault. Usually it is time delayed in nature, right? Inverse time characteristic is there. So this coil is energized and its contact closes, and then trip coil of circuit breaker is energized and this becomes open. Now, after this point, when breaker becomes open, the task of auto reclosing starts. So auto reclosing mechanism will wait for some time, right? Now, why this some time? So this time, as per IEC standards, because usually in our country we follow IEC standards. All the utility personals they follow IEC standards. So whenever the breaker becomes open, the utility person has to wait for some time delay. This time delay is decided based on reclaim time of the circuit breaker. Now what is reclaim time? Reclaim time is usually time which is decided based on, we know that whenever the fault occurs when breaker contact separates, then inside the breaker, depending upon the type of circuit breaker we use, let's say we use SF6 circuit breaker, or let's say we use vacuum circuit breaker. So depending upon the type of breaker, the arc quenching medium is there. And we know you have also studied at UG level that there is a arc quenching theories are also there. There are two main theories which we have studied. One is Slapion's theories and another is Cassie's theories. So according to Slapion's theories, whenever fault occurs and whenever circuit breaker coil receives the signal, there is a race between the rate of rise of restriking voltage and the rate at which the dielectric strength of insulating medium which is used inside the circuit breaker that is there. If dielectric strength of, let's say, SF6 circuit breaker, well, let's say we use SF6 gas because which is electronegative in nature. You have studied all the features, characteristic, right? So normally, let's say 70% of the circuit breakers are SF6 in our country. So when the dielectric strength of SF6 gas that becomes higher than the RRRV, rate of rise of striking voltage, right? It is dV by dt mathematically. Then the arc is going to quenched. If it is reverse, then arc is going to restrike, right? And that's why we have studied that restriking of arc takes place and then current chopping phenomena, right? Interruption of the small inductive current and capacitive current that is there, and usually most of the circuit breaker finds the difficulty in quenching such type of small inductive and small capacitive current. Anyway, we are not going in that detail. So your circuit breaker becomes open. Then whenever breaker becomes open, the dielectric strength of SF6 gas that is already utilized. So we have studied, right? When you study, if you have studied the high voltage engineering, right? What is the nature of the gaseous medium? Then it is going to regain its dielectric strength, but you have to wait for some time. So that time, so that it is ready for the next operation. So that time is nothing but your reclaim time, right? So that based on that there is a sequence, proper IC sequence is there. I don't know, I will show you if it is there in this PPT. And then once the breaker becomes open and reclaim time is over, then you have to reclose the breaker. You have to reclose the contacts of the circuit breaker. Now in our country, right, what we are doing at transmission level, we are going to reclose all the, let's say for example, there is a R phase to ground fault is there, line to ground, right? R phase to ground. So then what breaker is going to do? Breaker is going to reclose again. It is going to open all the three poles of the breaker, and then reclosing task comes. It is going to reclose only R pole of the breaker, right? This is known as single pole tripping facility or simple single pole tripping mechanism. Sometimes at distribution level in developed country also they are following same mechanism, but here at distribution level and at sub transmission level at 66 kV we are not following that strategy. What utility does? Utility is going to open all the three pole of the breaker, and then they are going to reclose all the three pole of the breaker again, right? that is there. In developed countries, if there is a fault in R phase, only R pole of the breaker should open, and then after some time, reclaim time, it has to be reclosed. This is the strategically difference between the developed country and our country, right? So now what is the advantage? If we reclose, and this is done automatically, right? Manually, it is not possible because you have to reclose it in 300 millisecond, 0.3 second. So this is done automatically using some sequence, right? It is known as auto reclosing sequence. Now, why this is required? So if in 300 millisecond, if a fault which is going to occur and you have opened the breaker, if it is transient in nature, right, it is going to die out because 300 millisecond divided by 20 millisecond, if you do that, then I think there are 15 cycles, right? Electrical cycles. So till now, I think most of the transient faults, they are going to remove automatically. They are going to die out. So once you reclose it after 300 millisecond or zero point 0.3 second, your system is healthy. No need to go for any interruption. No need to go for any maintenance. You don't need to send any lineman to find out the type of fault, what is the location of fault. This is not required, absolutely not required, right? This is what the utility that is utilizing nowadays, right? In at all 220 and above kV in our country, right? I don't know about 132 or 66 kV. Definitely at 66 and 11 kV they are not using. Maybe 132 kV they have installed as a pilot project at some place, but I am not aware with this. Okay. So if we just look at now, whenever the fault is there, right? Now, some of the conditions or situations are such that they look like a fault, but actually they are not a fault. For example, overload. It is not a fault, right? Overload means whatever equipment or the conductor we are using for transmission line, they are going to carry more currents. More current means the some percentage above its rated current. Let's say my conductor is designed for 100 ampere, and if it carries 110 ampere, 120 ampere, then we can say my conductor is overloaded by 110%, 120%, and so on. This is not a fault, right? Because when overload is there, when equipment or conductor carries or draws the current above its rated value, then the increase in magnitude, that is very slowly, right? It is not rapid. Whereas in case of fault, increase in magnitude is very rapid phenomena, right? Di by dt is very high in fault case. Sometimes you have inrush also, magnetizing inrush. When you energize the transformer, right? Let's say power transformer, 400 kV to 20 kV, right? Then usually we energize the transformer during unloaded situation. That means no load is connected. So secondary side load is not there, or maybe if it is there, lightly loaded is there. And then on primary side, we are going to energize the transformer. So according to the equation n phi equal to Li, so if you take I, then it is n into phi divided by L. So whenever you energize the transformer, leakage path of the transformer that is very slow, right? It is going to follow a small leakage path. So the magnitude of current is very high, right? Because it does not involve winding resistance and so on initially, right? After 5-6 cycles, when winding resistance is involved, then the current that is going to decay, and then your nominal current that is established. So this current, right, when inrush is there, it is 5 to 6 times the rated current. So this is also not a fault. However, if you have a relay or device which is going to sense the fault, then it assumes that it is a fault. So some discrimination is required, right, to identify whether it is a fault or whether it is an inrush situation. Same way power swing is also there, right? In transmission line, you have studied the load flow studies, right? Very well. Load flow, then you have studied the optimized load flow or power flow, constrained optimized power flow, and so on, right? AC/DC power flow. So when you have the power system network at transmission level, then because of the fluctuations in the power, voltage and currents are also going to be fluctuated. Let's say there is a fault on adjacent line. So obviously your neighboring line that is also affected. Its voltage and magnitude changes. This should not be detected as a fault. It is not a fault. Power swing that is going to die out after some time. It has some specific locus, right? Usually it moves, this locus moves from, let's say, first quadrant to the third or fourth quadrant, right, depending upon the situation. So that is also there, but this should be discriminated, right, with the fault condition. And the other fourth one, that is the prime mover failure, that is there. That means, sorry, whenever you have the failure of the turbine, we know that we are using the turbine at power station level. If you have, let's say, coal based power plant, then we use some turbine. If we have hydro based power plant, we go for Kaplan or Francis turbine. If we have diesel generator, we have diesel turbine. If we have gas based power plant, we use gas based turbine, and so on, right? So if prime mover or turbine that is failed, there is no harm to the generator, right? Am I right? Is there any harm to the generator if prime mover fails? There is no harm because my synchronous generator that will act as a synchronous motor. Earlier, what happens when prime mover is there? Synchronous generator is going to produce the power and it is going to deliver to the transmission line through bus bar. Right now, what happens if prime mover fails? My synchronous generator acts as synchronous motor and it is going to take the power from the system, transmission line, and so on. So there is no issue as far as the generator which will act as a synchronous motor, right? There is no harm as far as the transmission line is concerned. That is no issue. But the issue comes, that is the turbine, because if any of the case, if turbine fails, any type of turbine, right, coal, hydro, or anything, then that is going, what happens, if you do not take immediate action, right, within certain time limit, then the blades of the turbines, they may become corroded. So your blades of the turbine may damage. If you have hydro turbine, bubbles or cavitations are formed. If you have diesel or some other generator, then the fire may happen, right, because of unburned fuel. A similar same situation occurs in case of gas also. So this is not a fault again, right? This is a different phenomena. So this need to be discriminated. And last comes stalling, right? Stalling is a specific type of phenomena which occurs in induction motors, right? When you connect a very heavy load on the induction motor, then motor usually denies to start, or if it starts, then it works or it runs at 1/10 of the nominal speed. Let's say nominal speed is 1450 rpm, right? Then it is going to run at 100, between any speed between 100 and 150 rpm. So then what happens? Then it is going to generate the repelling forces and between the rotor slots and stator slots, and that is going to damage your, let's say, winding of the induction motor. So this phenomena is known as stalling, right? And it depends on whether you have started the motor, right, when it is in hot condition or cold condition. Cold condition means you started the motor fresh, and hot condition means you have started the motor, then you stop, and then after, let's say, some 15-20 minutes, you again restart it. So that is then the temperature reaches earlier than when you started the motor in cold condition. So that is the difference anyway. Stalling is also not a fault, right? So that also need to be discriminated with the fault situation. Okay, now I am not going to in the detail of all these things, requirements and all that, because this I think you have studied. Only thing which is more important is the economics, right? When you purchase the relays and circuit breakers, then economic part is very important. It is similar to when you purchase the cell phone, you want maximum features with minimum cost, though it is not possible, right? So that is not possible, right? Practically it is impossible. So somewhere, somehow, some point you have to compromise, right? Whether you want how many features and whether you want how many, what is the cost. So that you need to understand. So whenever you consider the, let's say, cost of the system is 100%, then cost of the protective gears, which includes your relay, CT, PT, wiring, everything, that should not be more than 5 to 10% of the total cost. Breaker cost is separate, right? That is not included here because that comes under the switchgear part. So that is not included. So this need to be followed. Okay, now just a minute. Let me check whether we, yeah. Okay, now just I am hurriedly going to uh, the different types of relays what you have. Now, if you just look at the latest generation of relays, right? I thought you must be aware of this. So this is digital or numerical relays, right? So it is usually compatible with the communication also. That is the thing. So it is compatible with IEEE C37.118 and IC 61850, which is your substation automation protocols. So this relay is compatible with this, and they may use the controllers or usually DSP controllers, right? And now the whatever is the above the digital or numerical relay, the relay available, that is IED, right? Is it known as intelligent electronic device? So they even the manufacturers are still using DSP processors only, but now they are trying to replace the DSP processor with FPGA based processors. But still it is at a research level. It does not have any, means nobody has installed in the utility or anywhere in the system. The reason why they are calling IED, because they can have the communication, they can have the protection, they can have control, they can have measurement, all these features, right? That is available in IED: measuring, measurement, protection, control, communication, right? Even some backup storage, that is also there, limited backup, right? So all these features are there. That's why the utilities are moving towards IED. Okay, now let me just share another PPT. Is it visible, this one? Can anybody tell me, is it visible?
Yes, yes, sir. Yes, sir.
Yeah, okay, fine.
Okay.
Okay. So now let us start with our original lecture concept. What is fault detection, classification, and location? So as I told you right earlier that transmission line, any transmission line is there that involves usually three major tasks: fault detection, fault classification, and fault location of the transmission line faults. Now you are aware what are the types of fault. All are transient or permanent in nature and mostly single line to ground faults, right? Though line to lines are there, but they are also very rare. 2 to 5% are the line to line faults, but very rare, right? So what is the requirement, right, for transmission line? The requirement is you detect the fault very fast. You have to isolate using the circuit breaker, which we are using SF6 or maybe some other type vacuum that is not used beyond 33 kV or at the most 6 kV. So now they are using some hybrid type of circuit breaker, which is a hybrid nature of SF6 with some other gas, right? And once you have isolate the fault or faulty section rather, then you have to classify the faults, right? That means which type of fault is it out of, let's say it is R2 ground, Y2 ground, B2 ground, R2Y, Y2B, B2R, or RYG, or YBG, or BRG, or RYB, or RYBG, right? So that you need to let's say identify, right, that which type of fault is there. Now, why this is important? Because the engineer, which is who is working in the utility, he or she has to send the lineman for the maintenance work, right? Repair work. Let's say he can tell now how the utility person knows that, okay, for let's say I have a 150-kilometer long transmission line and fault has occurred at 70 km, for example, right? We don't know, right? A fault can occur anywhere on the line. Now it has occurred at 70 kilometers. Now how the utility person knows that, okay, the fault has occurred roughly around between let's say 65 to 75 kilometer with some tolerance or error, right? Because you cannot always find out the exact location, right, with very precise value. So there is always an error. So he can tell the lineman, okay, just go to 65 to 75 km, identify the this string of insulators, and then the lineman can see that, okay, there is a fault, some maintenance need to be carried out. Or if it is, let's say, the what is the first task of the utility person? The first task is he or she has to operate the auto reclosers, right? And if auto reclosers he has to operate now, there is a debatable issue that whether I have to reclose the circuit breaker, pole of the circuit breaker once only, twice only, or thrice only, right? So only let's say there is a fault, I open the breaker and then I reclose it. Still there is a fault. Again, my breaker that is going to become open and remain in open condition. Right? So this type of situation is known as instantaneous trip lockout. After one operation, one reclosing operation, it remains in open condition. Right? That means some severe fault is there, which need to be cleared by the lineman by through utility personnel guidance. Sometimes, right, at now, whether we will go for single operation of the recloser or three times operation, that depends on the utility. Usually in our country or in developed country also, if you are attempting or if you have installed reclosers, auto reclosers at transmission level, then only single shot that is to be attempted, right? So whenever there is a fault, breaker becomes open, you reclose after 300 millisecond. If still there is a fault is there, then it is identified that it is a permanent fault and breaker pole that becomes open. That is there, right? So this is to be attempted by the utility at transmission level. At distribution level, you can go for three attempts. Fault is there, breaker becomes open, again you reclose it. Still there is a fault, again you open, again you reclose it. You can go for three attempts. And after third attempt, if still there is a fault, then your pole of the breakers remain in open condition. So this is the normal strategy followed by the utility. Now in our country, most of the circuit breakers are operated, or this we can say that they are gang operated circuit breakers. Right? Gang operated means it is not like D-gang or like that. Gang operated means the all the pole of the breakers they open simultaneously, right? At a time. So it is like that. Now simultaneously means whenever the all the three phases RYB they are 120-degree apart vectorially, and mechanically their coils are also vectorially physically apart. So the first phase comes, second phase comes after 120-degree, third phase comes after another 120 or 240-degree, like that. So they will have a common degree, right? Let's say 60-degree or like that. When the voltage is the minimum, right? What is the voltage? Voltage across the pole of the circuit breaker, when it is minimum, at that instant you are going to operate the circuit breaker, pole of the breaker, right? So this is not done again manually, right? This is done automatically. And this type of strategy or scheme, that is known as control switching strategy, right? Control switching strategy. So you use some dedicated processor. They are going to continuously monitor the three phase of the transmission line, and whenever fault occurs, this controller will tell that okay, this is the value or the degree among all the three phases. When you open, then minimum stress or minimum voltage across the contact of circuit breaker that is going to impose, so that your contact of the circuit breaker that is not going to damage. So this is done by control switching. Of course, we do have in our country, we do have control switching strategies at different voltage level. But still, at some of the places, we are still using pre-insertion resistors, right? You have studied at UG level, PIR, pre-insertion resistors. So the pre-insertion resistors means whenever the contact or pole of the circuit breaker becomes open, then the path of the fault current that is to be bypassed through the this pre-insertion resistor, right? That is there, but nowadays it is not used anywhere in the system. So this is all about how the transmission system or the transmission line works. Now, whenever there are two things possible, right? Whenever you want to detect, classify, and locate, there are two strategies possible. The one that is you directly, let's say, implement it using some processor, let's say DSP processor. You do it and then you operate accordingly, right? The second is if I wanted to go for, let's say, AI or ML based algorithms, then I have to do the modeling of the system, right? Because we know that, or you also know that any AI or ML based systems need these significant amount of data, right? Some for training purpose. So for that, you need to do the modeling of the transmission line or transmission network. So here you can see I have shown you a simple two terminal transmission line at 400 kV. It is you can say that it is a 128-kilometer line. This is a standard line used by utility in our country. It is used by GetCo only. And the fault data you can generate using any of the, let's say, tool. You can use PSCAD, you can use MATLAB, you can use any other software like DSpace or let's say Typhoon or any other thing, right? OpenRT, RTDS, let's say microcontroller box, anything, right? Any simulation network, EMTP, ETAP, anything you can use, right, for modeling purpose. Any type of software which you know. My power, right? There are many such softwares available for modeling purpose. Maybe you know better than me. So we use PSCAD, right? Because I know PSCAD. That's why I use PSCAD, right? It is not that I did not know any other thing. That's why I use PSCAD. Okay. So now you have to generate the fault data. Why we use such a such device? Because we want to generate the fault data, right? So if I wish to generate the fault data, then you can generate the n number of data. How you can generate the data? Let's say you can create the fault. Let's say this line is 128-kilometer long. So you can create a fault at different location. Let's say at the interval of 1 kilometer, 2 kilometer, 5 kilometer, right? Depending upon at what distance you want to create or simulate the fault, right? That is one thing. So this is one of the parameter, right? Variable parameter. These are known as fault parameters. Fault parameters means fault is going to occur at any point or any distance or any location on the transmission line because it is not in our head, right? So that is one parameter, variable parameter. Other parameter is fault resistance, right? Let's say if you have line to ground fault, it may occur through, let's say, some tree limb or some other thing. Let's say line to ground fault occurs on the RCC surface, asphalt surface, depends. So fault resistance also you can vary, and tower resistance also comes in picture, right? Whenever line to ground fault occurs, you can see that tower resistance also comes in picture because you remember cross arm and then the line to ground fault that is followed through tower. So tower has some resistance from 5 ohm to 50 ohm. This is also variable depending upon the environmental condition. That also you can vary fault resistance, right? Including the if you have line to line fault, let's say I have RY, YB or BR fault, then you have the and this is I told you about only one type of fault, RG. Same thing you can perform for YG, all 10 types of faults, right? Except open conductor. Open conductor is a separate fault. It usually occurs at distribution level, so we do not bother about that. Sometimes it is known as broken conductor fault also, but it usually occurs at distribution or 66 kV sub transmission level. So the thing is that you have to vary the location of the fault, right? That is one variable. Second variable is the type of fault, right? All 10 types of faults you can simulate it and you can generate the data, right? Let's say you have considered, for example, 128. So let's say total you have considered 30 different locations, right? Varying from 0 to 128 kilometer. So 30 is your the parameter, let's say your fault location variable. Then fault type, 10 types of fault that is fixed, right? Three line to ground, three line to line, three double line to ground, and one triple line or triple line to ground. So 10 types. So 30 earlier 30 location into 10, so 300, right? That is there. Then you have to consider the fault inception angle. At what angle fault occurs? Now, what is fault inception angle? Right? What is fault inception angle? So we know that whenever fault occurs on left hand side, I have shown one source VL, right? So if you just draw the equivalent circuit of this, then there is a source, AC source. Let's say E equal to Em sine omega t plus phi, right? And then there is a transmission line with parameters. Let's say you consider any parameter, let's say lumped parameter or medium line or distributed parameters for long transmission line, nominal pi model, nominal T model, depends, right? So line parameters are there, R, L and C. And then there is a fault, right? So whenever there is a fault occurs, what happens in the transmission system? Whatever is the energy, 1/2 Li square, that is to be transferred to 1/2 CV square, right? And because of that only the current magnitude that becomes very high. Even voltage magnitude also increases over voltage slightly. So fault inception, that is em sine omega t plus phi phi minus theta, right? So this theta, that is nothing but the switching angle or fault inception angle. When your voltage wave is passing, if you consider sinusoidal voltage wave, and let's say if it is passing at peak value, then fault occurs. If it is passing between 0 and peak, then fault occurs. And if it is passing through, let's say, anywhere from peak to lower side of the 0 half cycle, then fault occurs. So that fault inception or switching angle, that is also variable. So that you can consider 10, for example. So then 300 into 10, 3000, right? That is there. So this is all about the fault parameters, right? The 3000 data you can easily generate with simple, let's say, simulation. And then you can also consider the some source impedance variation, right? On left hand side, I have shown some source. 8 impedance also varies. Why the impedance of source varies? Because I have shown single, let's say, single generator, but it is a group of generator, right? Let's say 5, 6, 7, 10 generators are working parallelly, and depending upon the load, generators are switching in and switching out of the system, right? As per the concept of economic dispatch and unit commitment, which you have studied at UG or PG level. So you can also generate the data, right? Let's say some source impedance variation, you can consider 10 or 20, and then 3000 into 10.
Sorry, sir.
Yes.
Slide are not changing, I think.
Yeah, I have not changed the slide.
Okay. It's okay. Okay,
Yeah,
continue.
I will tell you when I change the slide, right?
Okay, sir.
Okay. So 3000 into let's say 10 or 20, you can consider source impedance. So accordingly 30,000 or maybe 60,000 data you can generate. These are the fault data, right? So this you can generate by varying fault parameters and system parameters, right? These two things you have varied, and you can generate. Even you can also consider of variation in the rotor angle, right? I have shown the bus L and bus R, local and remote end. So at that end, this voltage or bus, right, you have studied in load flow studies, it has some magnitude and angle. And that angle varies within certain limit, let's say 0 to 20 degree, 0 to 30 degree, both the sides. So that also you can change. If you control that angle, right, from local end and remote end, then you can also change the power flow. Either it is from local end to remote end, or it is from remote end to local end. So that also variation you can consider, right? It is known as a pre-fault power flow condition. You can simulate and you can generate n numbers of data, right? So this is there, right? How you can generate the several data. We can say fault by changing the fault and system parameters. Now I change the slide. I hope it is visible. So now whatever data we are getting, right? I have shown here some radial basis function neural network, right? This I did earlier, just 12, 13 years ago. But nowadays you can use some recent network like LSTM and GNN and so many other networks, right? Deep learning and so on. So that you can consider. And what that the methodology remains same, only the tool we are changing, right? So whatever is the data you have generated, right? Maybe 30,000, 60,000, 1 lakh data. That data you need to, let's say, acquire the data, and then you need to, what you have to do next is you have to normalize the data, because this data, whatever is acquired, right? You have acquired the data using generally data acquisition system. So this system is ADC, right? Analog to digital converters. And analog to digital converters, that there is a special feature or peculiarity that it does not take negative wave shape, right? So accordingly you have to acquire the data, you have to just consider the biasing also, and then what you have to do, you have to also normalize the data. So normalization you can do based on the per unit concept. You have already studied per unit concept. You have solved many examples, right? You can take base MVA and base KV. Base MVA remains fixed throughout the network, This KV that may change whenever transformer comes in picture. So that you can vary, you can consider, and then you can normalize the data. So once you obtain the data, you can normalize the data. Now, whatever normalized data are there, that data you have to let's say is available here somewhere after data acquisition system, right? You can see the cursor which I am moving. So normalized data you have to consider, and according to those normalized data, you have to also consider the values, right? Let's say you created R2 ground fault at 1 kilometer with the fault resistance 0.2 ohm, fault inception angle 30°. Let's say you consider one case. So then you know the what is the output of that? The output is, let's say, R2 ground fault. So then you can consider the output label as, let's say, 1. 1 means right R2 ground fault, and 2 means Y2 ground, and so on. Like that, 10 labels you can consider, right? And then now if I use all the 30-60,000 data for training of the let's say my neural network or any type of algorithm, then my algorithm that is stuck, right? It cannot handle those large amount or large volume of data. So then the important task comes, that is feature extraction. Feature extraction. That means you have considered, let's say, 3 voltage, 3 current. Then you have to consider that, okay, I am going to have only sequence component or sequence voltage or sequence component of current or any value. So let's say you have 20 features you have acquired. Now out of that you have to see that, okay, if I consider only out of 20 only 5 or 6 features, then I can train my algorithm efficiently, right? Without being overloaded by that neural network or that network, whatever it is. So feature extraction comes very that is very important, right? You can use different type of algorithm like wavelet transform, Fourier transform, principal component analysis, and so on, right? Short time Fourier transform, Stockwell transform, and so many transforms are available. You can use as a feature extraction, right? So once you have decided that, okay, whatever data which I have obtained normalized value of data, and I have only the, let's say I'm going to use only 5 or 6 features of those data, that I can give to my network, right? Neural network, whatever it is, your AI or ML based algorithm is there, that you can give it to your fault classification algorithm. And once this fault classification algorithm output is there, that means that algorithm is detected that, okay, the fault is R2 ground, then that logic you have to give to some decision logic. Decision logic means your controller, right? This all these things, your neural network based algorithm, decision logic, right, all comes under one controller, right? Because ultimately whatever algorithm fault classification algorithm you have implemented or you have deployed in the controller, whatever it is, usually DSP controller. So that output you can give to the logic, decision logic, and then decision logic also parallelly works on fault location part, right? That at how much distance the fault has occurred, and that logic is that command is also given to the decision logic. And finally, you can tell display, you can tell the operator or utility person, because this time you have already isolated the circuit breaker, right? It is a permanent fault. Now you can tell, you have to tell the lineman or the utility person or engineer that the fault, this is the type of fault which has occurred, and at this distance it has occurred. So it can send the lineman, and it can restore the supply can be restored by the line personnel as early or as quickly as possible. Okay. Now, whenever you consider all such any type of algorithm, pre-processing, feature extraction, right, or any type of AI ML based algorithm, then sampling window or sampling frequency is also an important part, right? So again, you have to refer to the Nyquist criteria that the sampling frequency should not be lower than the highest frequency component, 2 times the highest frequency component available in the network or the system, right? Let's say my highest frequency component is ninth harmonic, for example. So then ninth into 50 hertz, 450 hertz. So my sampling frequency should be always greater than 500 hertz, like that. So that type of Nyquist criteria you can consider, and you can select the appropriate sampling frequency or sampling period. Now nowadays most of the processor based relay, they either consider 4 kilohertz, 2 kilohertz sampling frequency, 4 kilohertz sampling frequency, or sometimes they may go up to, let's say, 8 kilohertz or 10 kilohertz also, right? This is also there. If they use some different type of relay, then they can go for this type of higher rate of sampling frequency also. Okay. Now, if you just look at right the waveform, right, I have used wavelet transform as a feature extraction part. So you can see that I have shown the first graph is the current magnitude. This is the instant where fault occurs, and then you have several post-fault cycles. From this instant to this instant, pre-fault period is there, and I have calculated some values, some coefficients, right? So you can calculate likewise any type of coefficient depending upon which method using. Here I have used two coefficients, A1 and D1. And then you can, I have calculated wavelet transform maximum modulus. And then you can see that once fault occurs, fault detection time, that is very small, right? And this is the pre-fault period, and this is the post-fault period. This is the threshold which I have used. And if this point exceeds this amount, right, then the fault is detected between this instant and this instant, right? So likewise, you can have this. So this is the different types of faults: AG fault, AB fault. You can see the two waveforms R and A and B. It is there. C waveform is below the threshold. So like that you can consider. And then you can consider the fault classification. So once the output of the wavelet, you can give it, of course, normalized in nature features. And then you can, let's say, define the output like this fault classification algorithm output. One normal condition, two line A2 ground or R2 ground, Y2 ground, B2 ground, and so on. So likewise, you can give the number 1 to 11, and you can, depending upon what is the output, the person, utility person, knows that okay, this is the type of fault which has occurred. So these are the certain patterns which I have simulated. It is pre-fault power flow pattern. You can see the voltage at local end, voltage at remote end, the P plus JQ, right, at between LR, at L and at R, right, in MVA. So that I have normalized later on. That and the parameters also I have selected several parameters. Now, whenever you want to, let's say any algorithm, if you consider, let's say AI or ML based, once you obtain the output, once you train it, right, then you have to test it. And when you have to test it, you have to, how do you know that whatever the training you have done, that is perfect? So for that, you need to consider several parameters, right, based on which you can tell that, okay, if this parameter is within this value, then I can say that the training done, that is proper, right? That is not the further training I have done. So here you can see that I have considered mean square error. I have considered the spread. I have considered the number of hidden neurons in the radial layer, number of epochs, and the training time, right, in seconds. So this I have done again 13 years ago. That's why the training time is in seconds. If you do it today, then this would be in milliseconds, right? That is the difference. But procedure remains same. There is no change in the as far as the procedure is concerned. Uh, okay, then you can also check the testing part of whether the fault has classified, your algorithm has classified the fault accurately or not. So that you can do it using by varying the load flow parameters, right? VL you can vary, VR you can vary, load power flow you can vary, right? At between the line at L and at R. So that also you can do that. And if you just look at the output of the classification part, then you can see that the output available, that is like this. Now you can see the first row. There is a test set AG ground, A2 ground or R2 ground fault. It has occurred at 5% of the line length from local side or sending end. Fault resistance I have considered 50 ohm. Fault inception angle 0 degree. And the actual value is this one, right? Which I know. And the desired value is this one. So all other parameters, you can see this second value and this second value, both are. So by taking the difference, you can calculate the error also. What is the mean square error? Now, always, if you look at B2 ground fault, C2 ground fault, right? Serial number 2, 3, 4, 5, 6, then you can see that at serial number 2, the value, actual value is 0.98, right? Or 0.99, and the desired value is 1. Similarly, at serial number 3, the desired value is 0.96 and the desired value is 1. At serial number 4, double line to ground fault, desired value is 0.99, whereas the actual value is 0.99, desired value is 1, and so on, right? For other cases. So you can see that always you are not getting 1 as the desired value, right? You are getting maybe below 1 or higher, slightly higher value of 1. So whenever you decide your desired value, right, then you have to give the range, right? Let's say if it is between 0.95 to 1.05, then I consider this as A2 ground fault, like that, right? So that you need to consider. And if you just look at serial number 1, you will get the actual value at, let's say, second element, here also second, but second B2 ground fault, you will get this element 0.9872 at third element. Here also third. So likewise, as you move from different type of fault, this value, that this element value also changing from first, second, third, fourth up to last, right? Which is triple line or symmetrical fault. So that also you can consider here. This is the response, right? In bar form, you can also, let's say, generate the response that at one particular type of fault, you will have the, let's say this is A2 ground fault, right, which is giving, others are almost close to 0. Similarly, the other fault, three-phase fault also you can consider. Maybe double line fault also you can consider. Maybe double line to ground fault also you can consider. So you can see on the y-axis you have the desired value from 0 to 1. Sometimes I have taken minus 0.2 to 1. And on the x-axis you have the different output of the RBFNN, that is 1 to 11, right, which you have considered. Now fault location. So once you have done the classification of fault, which type of fault has occurred, right? That you have done. Now the next part is the locate, to decide or to calculate the location of the fault, right? So similar thing, same type of data, training patterns you can use, you can normalize it, and then you can calculate, you can give it to the other type of algorithm, and you can calculate the percentage error, which is actual location minus desired location divided by length of the line, right? That is 128 kilometer in this case, multiply by 100. So you will get percentage error in percentage. So if you just look at the output, right, for LG fault, right? So then you can see that here you can see that the output, you can see the fault location which I have varied in first column in percentage from 15% of the total line length and so on, right? And then the load condition, I have changed the active and reactive power flow. I have changed the fault resistance. I have also changed the fault inception angle, and then actual and desired value of fault, that is also there. And last column indicates the percentage error. You can see that the percentage error remains below 5%, right? It is there, plus or minus 5%. And if you take the mod value, absolute value, then this comes in positive side. So this is how you can have the uh, location part. Similarly, for line to line fault, you can calculate the percentage error, and for all cases you can see below, let's say, 5%. Double line to ground fault also you can see, and triple line or triple line to ground fault also, it may reach up to close to 5%, right? And this show why it is so why it reaches the 5%, because I have taken minimum number of features. If I increase the feature, then this error may reduce, right? But again, you have to see whether by increasing the feature, your neural network or the AI ML algorithm should not be overloaded, right? That is also there. So that optimization you need to do. And then I have compared with the existing algorithms for fault classification and the fault locator network. So that you can see that I have compared with existing algorithms, and the proposed one, it is better, right, in terms of the error and all that. So that is there. Now limitations. So I used radial basis function based neural network. So as I told you, the neural network requires a large volume of data, right? So that you need to generate. If data changes significantly, and if there is a wide variation in data, then your output also changes. And sometimes it may possible that when you do or when you go for training, your training may not be converged, right? Because it may end up in local minima. So this is quite possible, right? At that time when I attempted this, and nowadays maybe if you use deep learning neural network, then probably this type of problem may not be there. As I told you, this type of neural network that remains black box. None of the let's say manufacturer has implemented any neural network based algorithm. They have not deployed in the processor, right? If you deploy neural network based code in the DSP processor, then it is going to hang up. So you cannot use DSP processor, which most of the manufacturers are using nowadays, right? Though I have used some other technique also, support vector machine, right? So it is again the feature extraction we have done, and then we have used the support vector machine, right? So different types of the this type of different types of the you can say algorithms, at feature extraction level, and at the actual classification and location level, you can use it. You can also generate the fault data automatically, right? You need not to generate each data manually. So if you are very well in programming, you can do it, and you can generate the, let's say 10, let's say we have n number of variables, then you can generate the 10 raised to n data sets, right? Automatically. So I did it automatically. I wrote a program, and then I generate the data. So you can see that I have generated around the total patterns 1080, a very small number nowadays, but at that time it is significant, right? Training data is 4800, testing data 1080. And we did feature extraction also. Instead of some other wavelet, we use discrete wavelet transform, and then the output of that is given to SVM. And we use the this DWT, discrete wavelet transform, and whatever the features are available, you can see F VIA, F VBIB phase wise. That I have given to three different SVMs phase wise: A phase SVM, B phase, and C phase. Sampling frequency we have used 4 kilohertz, which is used by most of the utility. And then we have suggested some fault classification algorithm. We have suggested faulty phase identification also, so that that can be used for auto reclosing purpose. Because if I want to, let's say, reclose the R pole of the breaker, then I must know in which phase fault is there, which phase is faulty, whether R phase, Y phase, B phase. So this will also tell that which phase is faulty. And phase fault is not alone sufficient. You have to also see that whether the fault involves ground or not. So this is also covered here. And then faulty phase identification, that is to be done using three SVMs, A phase, B phase, and C phase. And different types of faults we have considered, and we have classified the each fault, right? That is there. Ground detection we have carried out using zero sequence component, right? We can easily detect whether the ground is involved in the fault or not by using zero sequence component. So I have used the ground detection index, which is made up of the zero sequence component, so that we can easily detect it. And this you can see that the whether the ground is involved or not, that you can observe from RG, RYG, RYBG, RY, right? The ground detection value is very low in case of phase fault, whereas in case the fault which involves ground, the value is significant. So that is how you can discriminate it. Support vector machine you can use for classification purpose. So it is again the you can use linear classifier as well as nonlinear classifier. I have used a nonlinear classifier, so that you can use it and you can separate it out the one class of data with other class of data, which they call it hyperplane. So anyway, I am not going in the detail of this, right? We have used several parameters, right, to observe the whether the SVM is giving correct output or not. So linear, polynomial, Gaussian, and sigmoid. These four functions we have used. And then we have selected the parameters also, various training and testing. These are the, you can say the parameter selection, and you can see the this gamma and the degree. These are the parameters of SVM, right? So which parameter I have to select, that you can see I have prepared a table and then I have identified that the parameter which gives highest accuracy, that we can select. So likewise you can do that, and then the classification part also you can do. For each phase you can see the accuracy is given. Though it is not up to the mark, sometimes it is giving 90%, sometimes it is giving 97%, 100%, right? It is always variable. Right, and the fault wise also you can see I have given the accuracy for which fault. Let's say RG fault, total 108 cases are there. Out of 108, 102 are classified correctly, and you will get this accuracy. Likewise you will have it. And the fault location, you will have the percentage accuracy also, right? And that also, that is to be identified. So we can say that we can use any algorithm or any method as a feature extraction, and we can use any algorithm like neural network, support vector machine, relevance vector machine, or any other deep neural network, just to classify. The only thing is that the main disadvantage is this all such type of algorithms you cannot deploy practically in the controller, right? Uh, I cannot say you cannot deploy. If you use FPGA, then you can deploy probably, and that I am working presently on that. So I think these are the papers which I have considered for this. Any question? I think Ravi. Hello.
Yes, sir. Yes, sir.
Yeah, I think I have done, right? So if any quick question is there, one or two, I can answer.
Yeah. Please, participant, please, if you have any question, you may ask. You can raise your hand. We can unmute you. Hello, dear participants. If anybody have any question, you can ask question to our resource person, Dr. Bhavesh Bhalja, sir. Yes, Eknath bhai. Sir, you can see chat box. There are
Okay, let me just check.
AI ML algorithm can be used in numerical relay practically.
No, it is not used.
Okay. Parthiv, but yes.
I cannot see the chat. I don't know. You have to
Okay.
read it.
Okay. Okay. Eknath bhai Tarwariya.
Yes, Mr. Eknath Bhai, please ask your question.
I think it seems that there is no question. So
Oh,
Sir.
yeah, yeah.
Sir, one of the question is there in the chat box. In which type of code can be used for programming?
Which type of
Code. I think the environment is asking you.
environment? You can use any environment, any controller, right, which supports AI ML.
Okay, any? Okay. Okay, I think there is no further question. Uh, Thank you very much, Dr. Bhalja, for a very interesting and detailed understanding on departing of knowledge to our participant regarding faults and power system faults and AI applications. Thank you very much, sir.
Yeah.